Okay, so we're going to talk about speed time graphs. You know 3 different types of speed time graph, Lauren? Yep, 2 seconds. Title is speed time graphs, yep. That's your title. Types of speed time graph. So looking at what types of speed time graph we've got, so you get your heading, speed time graphs written down, and we're going to look at what different types we are going to need to use. Okay. So 3 different types of speed time graph. Different ways they might look. So a speed time graph can be drawn very basically as 2 axes, speed and time. Okay? Now wait till I finish before you copy it down. Let's have a look at this. So we're going to do 3 different types of speed time graph. On the axis, time always goes on the bottom and speed always goes up and down the left hand side. So V is on that side, time is on the bottom, V and T, V and T. Now T is measured in seconds, V is measured in meters per second, as always. Okay? 3 different types. So 3 different types we're interested in. First one we're interested in looks a bit like this. Second one we're interested in looks a bit like this. And third one we're interested in looks a bit like that. Okay, so there's the 3 different types of speed time graph that we're interested in. You could have any combination of these. They could be mixed up, there could be different parts of it, and we'll look at that in a minute. And we'll use a little doofus to answer some questions on it. But there are 3 different types of speed there. Let's say it's graphs 1, 2 and 3. This is graph 1. What does graph 1 show us, Nicholas? Something accelerating, but in more basic terms, something's going faster or getting faster. Starting off at 0 and working its way up. Okay, so this object here is starting off and getting faster. It is accelerating. Good. It's accelerating. So this object here is accelerating or getting faster. This one here, what's this object doing in this speed time graph? Sarah? Constant speed. So it's not accelerating, it's not decelerating, it's going at a constant speed. Gillian, pay attention just now. So this one is constant speed. And this last one here, what's happening to that one? Ailey? Decelerating, or what else can it be called? Slowing down, or or getting slower. Slowing down, getting slower, okay. Decelerating is another word for what? Deceleration doesn't have a symbol. Jordan, put pencils down. Everyone put your pencils down. I'll ask you right in, I want you to pay attention. Okay, deceleration is another word for what? Negative acceleration. So if the acceleration turns out as a negative number, then that's a deceleration, it's slowing down. So it's actually accelerating, but in the opposite direction from the way you're moving. So if I'm moving forward and getting slower, my body is actually accelerating back the way. Okay? Decelerating forward, accelerating back. So decelerating is also a negative acceleration. So that would be, and we could write the symbol negative like that, acceleration. Okay, so there's the 3 different types of graph that we've got. And now what we could do is we could put them all together and we could get one big speed time graph to show the motion of an object over a longer time. It could show it speeding up, slowing down, staying the same for lots of different parts, and you'd have to say which bit's which. Siobhan. Okay, other piece of information we need to get from this. Okay, not only do we need to be able to identify the 3 different graphs, we need to be able to use the 3 different graphs. Okay, so this first graph here, what can we, if we get given numbers on the axis here, what could we calculate from this first one? What could we calculate? One. Distance? How could we calculate distance? Speed and time, so you know how fast it's gone, the length of time. You can calculate distance, that's good. Right, but how else? What else could we do with this? We can obviously, can we calculate acceleration from this? How? What bits of information do we need? Lily?
No, final speed and initial speed.
Final speed and initial speed and the time. So for this we can get, we've got final speed, initial speed, so here could be final speed, here could be initial speed, and then the total time taken for the whole lot. This one here, well, final speed and initial speed are the same, so acceleration is 0. And this one here, you get starting speed, final speed, total time taken, and that could get your acceleration in the negative direction as well. Okay? we can also get distance from these graphs, right? If I want to know the distance travelled by an object, let's say the middle graph here. This middle graph, if I was to just put a dotted line down here and say that took 10 seconds and that's 10 metres per second, how far has the object travelled? Okay, in fact, let's just do that on your default. Right, so what, now you're registering devices, what would be the distance travelled for the second graph there? What's the distance travelled? Second graph, let's work it out. 10 seconds at 10 metres per second, what is the total distance travelled?
What do you put a symbol?
No, I just want to know a number. Remember, it's a constant speed, so they're not increasing or decreasing speed. Distance travelled is what? Do you know? Oh, okay, so 10 seconds at 10 metres per second is quite clearly 100. 10 seconds at 10 metres per second, okay, so
Not working.
Okay, so Jordan and Craig. Jordan, why 20? Still asleep. Right, we'll wake up. Craig? So I thought you pressed your Aye. That's what they all say. I thought I pressed your brain. That's what I was going to say. Did you ever do that in primary school? Put your hand up. And then somebody, you get it wrong and then somebody else gets it right. That's what I was going to say. Ah, you weren't. Okay, so it's 100. Now, look at this graph here. Looking at the middle one, how do we get 100? What do we multiply by what to get 100 in this graph in the middle? Stuart, show me. Just tell me, what am I multiplying by here to get the 100? Average speed. It's not average because it's staying the same, so it's just speed by the time. But what parts of the graph am I multiplying together? All the parts of the graph. Right. Where are you getting numbers from? The what?
The graph.
Can't hear you. Stuart, say again. Line at the top. This line? Right, so how can you get 100 from this line? Come on. The value of the line. A line's a line.
Just do V times T.
V times T. Ricky, Gillian, where am I getting the V and the T from? How do I know?
On the board it says 10 and 10. It says 10 and 10.
Right, okay, so bite my head off here. It says 10 along the bottom and it says 10 up the side. Okay? Now, what shape is this?
Square.
A square. Okay, what am I calculating of the square?
The area.
Yeah? The area. Area. Yeah, right. The area.
That's how you really actually see
It did because it's
it.
Okay. Right, so the area of the square. We are calculating the area of this square. So the distance travelled here is the area of this square. Okay? Right, let's look at this graph here. This is, I'll say this is 10 and that's 10. What is the total distance travelled in that one? 10 and 10.
Oh! No! X and T.
Oh.
Come on. That's what they'll say. Okay, so 5, 100 and 50. Sorry? Aye. Correct answer, 50. Okay, Siobhan, why 100?
Because I thought it was just 5.
Hey, shh. Hey, stop talking. What?
I thought it was
Total distance travelled. Yep. You're right. It's total distance travelled. But this object's starting off at 0 and accelerating up to 10 metres per second over 10 seconds. So it's not going at 10 metres per second for 10 seconds. It's going at 10 metres, it's getting to 10 metres per second after 10 seconds. So, what have we calculated here, Kane?
calculated the distance and you have it.
Okay, but how do we calculate distance?
You do v times d.
How do we calculate
Do
distance?
that one v times d, but in this one it's only like not
Area
exactly.
Come on. Everyone's trying to tell you, Kane. Area under the graph.
I'm getting that.
This distance travelled equals area under the graph. Okay? Pardon? What did you say, Craig?
It's the same, you can work it out.
That's not the same as that, no.
It's just half.
It's a square, so that half is the same as that half.
Right, we're still in it. Half length times breadth
So you
will
just
give you the area of a triangle.
and then half.
Okay, so what we've got here, we've identified 3 graphs. We've identified that you can calculate the total distance travelled by calculating the area under the graph, and you can use the graph to calculate acceleration by picking out the different points. Okay, so let's just get this in your drawer. So there's our 3 graphs, and we say total distance travelled equals the area under the graph, and I've shaded that bit in to show you what the distance travelled would be. So for this one, the total distance travelled would be distance would equal 100, and this one, distance would equal 50. Okay, and we've worked them out. Okay, so speed time graph for a skydiver, and that's going to allow us to test and talk about accelerations and decelerations and what's happening. It also leads us on to the next bit we're going to talk about, which we start talking about forces again. Start talking about balanced forces, unbalanced forces, etc. So let's just draw our axis to start with, so we know speed and time. So nice big axis here. You've got speed and you've got time, and we're going to have 0 here. So as somebody jumps out of a plane, what is their initial speed as they jump out of a plane? Okay, what's the initial speed, Nicholas? 0. We're standing in the plane, they go to jump out, and just at the moment they step out of the plane, their speed is 0. So they will start off at 0 down here. Okay, what happens when somebody jumps? So they're going to start off down here. What happens when somebody jumps out of a plane? What? Has anyone die by jumping out of a plane? No? No? Has anyone get issues about people jumping out of planes? Just in case. Just a bit late now, as you all start crying. Anyway, so we're talking about Hollyoaks. That doesn't count.
That was sad.
Sad, yeah. Very sad.
I think that's the only time I ever watched Hollyoaks.
Right, what happens when somebody jumps out of a plane? Lily, to their motion. What happens to their motion? What do? They stay still? They fly? They fly! For the benefits of the camera, Lily is pretending to fly. Well, they don't fly, Lily. What do? They speed up. They speed up. Okay. They slow down.
No, they like. No,
They fall really quickly.
See when you first.
You go up. You jump out of a plane, you go up.
No, listen.
Sorry,
When you
I'm
jump
listening.
out, you go down, then you put a parachute, you go up the way.
No, they don't.
Yeah, you do.
You don't. No, you
You
don't.
You have like half a second when they
Don't.
I'm
I'm sorry, wait, let me tell you. Let me tell you. When you jump out of a plane, right, you speed up, correct. When you pull the parachute, you don't go up the way, you just don't fall as fast. So it looks like you're going up, but you're not going up.
It's like, oh, it's also wet. Oh, you stopped.
No, you do. Me.
I'm a bit slow.
Right, okay, so they're going to speed up. Are they going to speed up to a really high speed, Siobhan, or a low speed? High speed. So they're going to speed up to high speed. So this is going to get up to a really high speed. Now, so what happens? Does it just keep accelerating?
Unless
Why not? No, it's not open the parachute yet.
He reaches
Oh,
the terminal
he's nearly
velocity.
dead, he's nearly there.
No, it's nearly where? Nearly where? Nearly hitting the ground. No, okay.
When he's falling, he's like, he'll make his equal speed.
He's what?
He's equal speed. Like,
Equal speed?
yeah.
What
with his
equal
weight,
speed?
like with his weight and like he won't be able to fall in.
Do we know the word for this?
Terminal velocity.
Craig, would you like to explain to the class what you mean by terminal
It's
velocity?
like
So speed.
the fastest that an object can fall.
Right, just
Because of gravity.
to take a little side here, if I draw a little box, this is called a free body diagram, right? This is the person as he jumps out of the plane. The person's weight is down the way. Listen, Okay? Now, is there any forces that are going up the way? Friction, air resistance.
Oh, is this the thrusting thing I was talking about?
I think we should watch a video of someone jumping an airplane.
Thrusting.
I know. Oh, like...
What? Please! Enough!
No, what is it? Is this the
You've been phoning Gregor again.
Stop.
Anyway,
I know.
so weight down the way, friction up the way. Now what does that friction depend on? What is the amount of air resistance? Take your hand up, put your hand in front of your face. Move your hand slowly. Do you feel any air on your hand if you move your hand very slowly? No.
Yeah.
Move your hand quickly. Do you feel air on your hand if you move quickly? Do you? Nicholas?
I feel less.
Stop! So, what affects the amount of air resistance that you feel, Nicholas? The faster you go. So, the faster this guy's going, in this diagram here, the faster the guy's going, the more air resistance he's going to feel. So it gets to the point where the air resistance balances out his weight. Because he's going so fast that the air resistance is actually balancing out his weight, and then forces become balanced. We're going to talk about balanced forces soon. Okay? And at that point, he's going to reach a terminal velocity, and that terminal velocity means his speed will be constant. So, at this point here, his speed is constant. Right. Now what happens? Now what happens? So this is him travelling at a terminal velocity at this point here. Now what happens? What's he wanting to do now? Okay. Opens his parachute. Now what happens? You do not go up the way when you open a parachute.
Well, it looks like you do. He slowed down.
Do you know why it looks like you do? Because the guy that's following them in the camera does open his parachute at the same time. If they both opened the parachutes at the same time, they would stay together. Just the fact that the guy opens his parachute too quickly and he goes, oh! And you open mine.
How can you hold your hand out?
No, you put it again.
I didn't know. I was wondering how you actually video that.
Just drop the camera down with us.
Just drop the camera. Right, okay. So, what's going to happen to his speed when he opens the parachute, Ellie? Speed's going to go down. Yep. So the speed is going to go down. So his speed is going to drop down the way. Now, is it going to go all the way down to zero?
No.
Why not, Lauren? It's not stopped yet. All a parachute does is slows you down. It doesn't stop you. It just brings your speed down to a speed that you can hit the ground with. Okay? You can't hit the ground with this speed. You can hit the ground with a slower speed. So this will hopefully drop him down to a speed that he can hit the ground with. But he's not hit the ground yet. So what does he reach again? Sarah? Before he hits the ground, he's going to reach another, what do we call this bit again?
No, I quite.
Known as, Craig?
What?
Terminal.
Oh, that terminal velocity.
Terminal velocity. He's going to reach a second terminal velocity because his parachute now has created another huge amount of air resistance. Okay? Second terminal velocity, and then when he hits the ground, he's going to hit the ground with that velocity, and he's just going to stop.
No, I think I did either.
Okay. Right, there is the motion of somebody jumping out of a plane. Now we're going to label the parts, and we're going to talk about which bits are accelerating, decelerating, constant, etc. Okay? So on this graph now, you've got labelled A, B, C, D, E. Okay, and you've got A, B, C, D, E on your keypads. Can we do more than that, Wonder? So, between which 2 points is the object accelerating? Between which 2 points is the object accelerating?
Is it okay to do it in order?
That doesn't matter. Okay, who put A?
I put F-A.
F-A?
Can't you both put E after minute?
You don't know anything.
Okay, who put A? Jillian?
Honestly?
No, you didn't.
Honestly?
No, you didn't. Okay, so between A and F, or F and A, is your the object is accelerating, right? We know that one. Okay. Between which 2 points is the object decelerating? Don't do that.
Oh, how do you cancel it?
What? Oh, you need to press send.
Decelerate.
Decelerating or with a negative acceleration.
Mine doesn't, because I thought it was D.
B and C, good. That's fine.
Oh, yeah. Mine doesn't.
No, it's not supposed to do that, Jillian.
Oh, doesn't do what?
It doesn't shake.
Right, shh. Hey! Stop talking. Between which 2 points is the object moving at a constant speed?
What was the question?
Between which 2 points is the object moving at a constant speed?
Oh, there's 2. Oh, no.
You pick one. Pick one pair.
You can only pick one.
That's fine. I only want you to pick one pair, Lily. Really? Pick
Pick
one?
one. Pick a one. Pick a one.
A, B, or C and D. Good. That's fine. Right. I'm going to put some labels onto this with numbers. So now I put the scale on it, from this graph, I should now be able to calculate accelerations, decelerations, distances travelled. Okay? So, can you give me the acceleration between points F and A? What is the acceleration between points F and A? We know now that we can calculate acceleration and deceleration from this graph just using A equals V minus U over T. So we can use A equals V minus U over T. Make sure T is the time taken, not the total time to get to one of the points. Now, what other piece of information we can get from this graph is the distance travelled. Okay, can you calculate for me the distance travelled? What we're going to do is we're going to find the distance travelled between each point, and then we're going to calculate the total distance travelled by the object and the whole thing. Okay, so let's start off with the first part. And we're running out of time. Finish this off next day, get the total distance under the graph.